Hi, in this video we will quickly review how the exponential expressions are defined and what are the laws of exponents. Well, let us assume that we have a positive real number, any positive real number, and we want to define or see how to define b to the power x for all real number x. While b to the power x, we call that x exponent, and b the base. So base needs to be positive, but we want to be able to write b to the power x for general x. Well, how do we do this? We know how to deal with this when x is a positive integer, like n, 1, 2, 3, 4, any of those numbers. Then b to the power n, this is very easy algebraic notation. So basically you multiply b to itself n times. So b to the power 2 means multiply b to b, b to the power 3 multiply b to b to b. And well, specifically you see that b to the power 1 is b itself. Well, that is integer, positive integer, but what about another integer which is 0? Well, b to the power 0 is set up to be equal to 1. There are very good reasons for that, but know that any base to the power 0 is 1. How about negative integer? Something like -2, -3, and so on. So when we have b to the power -n, what we do is, or what we mean is that you first reverse b, then find the power of power n of that. So either make this one, or you will see me writing this for some reasons. So if you reverse b and then find the positive exponent of that, so you see here this is negative. When I reversed it or find the inverse of the base, I drop the negative sign. That will be the same as 1 over b to the power n, and well, that is same as, well, b times b goes to up to bn times in the denominator. So by this, we know that how to find b to the power -3, -4. Well, we can go a little bit further, and well, we can find that when x is a rational number. So rational numbers are numbers that you can write as fractions of two integer numbers. So b to the power n over m. What does that mean? So we are assuming here is m is positive. If the denominator is positive, then we can write this as mth root of b to the power n. And by mth root, recall that mth root of a box is a number whose mth power is equal to box. So when you power that guy to the m times, you get the box back. Okay, this is the end of the way we can do the algebraically these kind of defining exponents. But how about rational exponent, irrational exponent, sorry, irrational exponent? The numbers in the real line which are not ratio of two integer numbers, something like root 2 or root 3 or pi, and there are infinitely many of those ones. How about those ones? Well, this needs a little bit very advanced calculation, or something that we cannot go into the details at the moment. But what I want you to say is that b to the power something like b to the power root 2 cannot be computed by doing just finite things. What we need to do is the approximation. So first, we know that root 2 is a number, well, 1.41421356. It never ends. No one can write finitely many and then say it's done. But this can be approximated by small pieces of fractional decimal numbers. So when you have that, then you first find b to the power 1. Then you go a little bit further, find b to the power 1.4. Then find b to the power 1.41, and then go ahead b to the power 14142, and continue this process. Well, you may say, well, what does b to the power 1.4 mean? Well, remember that b to the power 1/4, I can write it as b to the power 14 over 10, and this is the nth root of b to the power 14. And the other one is b to the power 141, the 100 roots of that. And then for the other one, let me just drop one of these. Yes, and then this is 1000th root of b to the power 14. And if you do compute these things, because these are things that we can do, and if you do this numbers that we are finding, they will get closer and closer to a number. Whatever that number is, we are going to call it b to the power x. And that's how we define b to the power all real numbers. So this is how b to the power x is defined for all real numbers x. At some point, well, some of these are not easy, but there is a way to do it, and I just wrote main steps of how to find those numbers. Well, when you do all those things, then there are laws of exponents that without knowing how to compute those ones, you can use these laws. First, b to the power x and b to the power y. So when you multiply two exponential expressions with the same base, you can write one base and add the exponents. The second one is that when you divide two exponential exponent, then which they have the same base, you can write b to the power the exponent of the numerator minus the exponent of the denominator. The third law is when you have exponent of an exponential expression. So b to the power x to the power y, this is b to the power xy. And the last piece is that, well, if you're dividing two exponential expressions with the same exponent, this will be b over a to the power x. Well, this last one has a multiplicative version, which is a b to the power x, a to the power x is the same thing as ba to the power x. These are the rules that you have to know very well, and you have to be able to use them when it comes in computation. So there are two remarks that I want to mention here. First thing is that note the difference of b to the power x to the power y and b to the power x to the power y. These are completely different things. What the first one means is that first find x to the power y, that is a number, put it as exponent of b. Second one says first find b to the power x, that's a number, now you can find the exponent of that. Well, to see an example that these guys can be completely different numbers, see 2 to the power 3 to the power 2 and 2 to the power 3 to the power 2. This guy that doesn't have any exponent, it means that this is 2 to the power 3 to the power 2, and this is 2 to the power 9. However, this other one, this is exponent of an exponential expression. So this is 2 to the power 3 times 2, which is 2 to the power 6. And as you can see, those are completely different values or different numbers. The second remark is that, well, see the property, the second law. So b to the power x, b to the power y is b to the power x minus y. Using this, what we can write is that 1 over b to the power a number, you can see this as b to the power 0 and over b to the power y. This is b to the power 0 minus y, and this is 0 minus y is negative y. And you see here that in general, if you bring something from the denominator to the numerator, you have to multiply the exponent by a negative sign. This is basically what we did for the negative integers up here for just a specific case. In general, that's always true. If you bring a number from the denominator to numerator, you have to multiply the exponent by a negative sign.